In the last class, we have discussed the Nernst distribution law. According to this law, when we take two immiscible solvents and a solute which is soluble with the with that solvents, and the distribution of the solute between these two immiscible solvents in contact with each other occurs in such a way that the ratio of concentration of similar molecular species in two layers at equilibrium is a constant at constant temperature and irrespective of the total amount of the solute and independent of any other molecular species present. This is distribution law. So the distribution of the solute between two immiscible solvents C1 by C2, concentration of solute in first solvent to concentration of solute in second solvent, that is C1 by C2 is a constant. Consider a distribution system. And this now today we are going to discuss the application of this distribution law to systems in which the similar molecular species is not agreed. One condition of distribution law is that this can be applicable to similar molecular species only. That is, the no association or no dissociation of the solute in any of the solvents. But here we are going to discuss the conditions in which and what happens when the solute undergoes dissociation in one of the solvents or association in one of the solvents. At first, let us discuss the association of solute in one of the solvents. Consider a distribution system like this in the diagram. Here we have solvent 1, solute A, no change in C1 and C2. Solvent 1 and solvent 2, these two are two immiscible solvents, and we are taking a solute A, which has as it exists as such in solvent 1, and it associates in molecules of A associate to form AN in solvent 2. So total concentration of system is C1 is of A in C first phase first is C1, and the total concentration of A in phase 2 is C2. So the equation for association Na is equal to gives and gives An, and the equilibrium constant for this reaction, that is Kc is equal to An, concentration of products divided by concentration of reactants. Concentration of products An divided by A raised to N. N molar concentration of associated form, A molar concentration of normal form. So An is equal to 1 by Kc into An. Rearrange if we rearrange the equation, A raised to N is equal to 1 by Kc into An, or A is equal to nth root of 1 by Kc into An. So A is a constant. So A is a constant into concentration of A in one, that is equal to a constant into nth root of An. Since 1 by Kc is also a constant, it can be taken as a constant into nth root of An. An can be taken as C2, since it is the concentration of the total concentration of the solute in the solvent 2. So A is a concentration of A is a constant into nth root of C2. On applying partial law for similar molecular species, C1 is the concentration of A in phase first divided by root of nth root of C2 is equal to a constant, and using and this is the distribution law that can be applicable to solute which undergoes association in one of the solvents. Using C1 and C2 for several experiments, we are doing several experiments by putting different values for N. For example, n is equal to 1, n is equal to 2, n is equal to 3. 2, 3, 4 an association of only 2, 3, 4 is uh, relevant. So n is equal to 2, 3, 4. The ratio C1 by nth root of C2 is calculated in each case, and the value for which the ratio remains constant. C1 by nth root of C2 remains constant gives the value of n, that is the degree of association. So distribution of, for example, another one example is distribution of benzoic acid between water and benzene. So it's in that case we repeated the experiment with by putting n is equal to 2, 3, 4, etc. And we found that C1 by nth root of C2, for that this C1 by nth root of square root of C2 remains a constant, showing dimer of benzoic acid in benzene. So benzoic acid is a dimer in benzene. Next is the calculation of degree of dissociation of a solute in a solvent. Calculation of degree of dissociation, and this solute undergoes dissociation in one of the solvents, and in solvent 1, phase 1 normal concentration of A is C1, and in solvent 2 the total concentration of A is C2, where alpha is the degree of the dissociation, and the fraction of top degree association means total of number of moles of solute that undergoes dissociation. So initial concentration is C2. So A gives and gives X plus Y. That is C2 into 1 minus alpha, C2 alpha into C2 alpha. The concentration of undissociated molecules in solvent 2 is equal to C2 into 1 minus alpha. Applying distribution law for similar molecular species, C1 by C2 into 1 minus alpha is a constant. Example, dissociation of oxalic acid in water, the succinic acid in water between ether and water. These are examples for systems in which the solute undergoes dissociation in one of the solvents. Oxalic acid in water, dissociation of oxalic acid in water, and succinic acid in water between ether and water. System is ether and water, two immiscible liquids, and succinic acid undergoes dissociation in water. And this, that's all about the systems in which the solute undergoes dissociation in one of the solvents or association in one of the solvents. Thank you.